Alrighty, everybody. Good morning. Uh, Looks like most of the technologies decided to fail. Um, in fact, yeah, so the recording should be fine. Let's cross our fingers for a working recording where we've got audio and we've got closed captions. That's the important thing. And then for the live stream, you should be able to hear me. You won't be able to see me. I'm very sorry about that. Not sure why what worked relatively perfectly last week decided to up and not work this week. So let's dive straight into things then and try and make up for lost time. We lost 6 minutes there. So just some quick housekeeping then is that mostly what we got through last week in the lectures was just an introduction to the unit. And we also had a bit of a look in a live demo at connecting to the Azure cloud there. So just make sure that you do click all three links that are available to you on Milo, even though we're only using one virtual machine in these early tutes. Very, very soon you're going to be using all three, and I want to disable those links. It's okay if you really miss this, I'll give you a link later, but I'd rather everyone got through and clicked all three invite links that are on the guide page. And if there's a really nice person in the chat wants to link us to the guide, that would be amazing. Otherwise, I'll provide that link later on. Remember, it's not an invite link. It's not an invite in an email. There is a Milo page where you've got to create all three of your virtual machines. Slightly less important, but you may as well while you're there, is go to the guide for GitHub, which is where you can click links to create all your repositories for that. And just while I'm talking about GitHub, I did some announcements earlier or yesterday or the day before, I think it was, about updating your tutorial base code. So just make sure you pay attention to those. The idea is that the GitHub repositories for the tutorials are going to have some base code in them. They already do. They've got that little index page that we saw last week. But as I work my way through updating the tutorials, I'm going to be adding more and more base code into each of the weeks. The way that I get those code changes to you is through what's called a pull request. Anyone in the chat used a pull request on GitHub before? Anyone? Yep. Cool. So don't stress if you've never heard of a pull request before, but it's a useful thing for this unit in that it gets you updated code for your tutorials, but it's also, in a roundabout fashion, a useful thing for your learning that in the real world, quote unquote, you will be doing, you'll be understanding the concept of a pull request. Those are fairly common in software development, right? Where someone else has made changes to your repository and they're requesting that you pull their changes. That's why it's called a pull request. And so I will have made and will make pull requests throughout semester to say, I request you to pull changes when the tutorial code updates. But all these lovers of Git in the chat, or just anyone, what happens if you have changed a file in your tutorial repository and I have also changed a file in the base code? What do you get when you try and pull those changes? Everyone's favorite thing, a merge conflict. Normally, a merge conflict can be pretty manually resolved. For whatever reason, in this unit with GitHub Classroom, you guys don't have permission to manage your own merge conflicts. So if that happens to you, just send me a message and it's going to be a pain. So I'm going to try and only update files that you won't have touched yet. So future tutorials. I don't know why. Even when, yeah, John, I don't know why. Even if I give you admin access to your own repository, Josh there, I did that manually for him and he still said it didn't work. I'm going to double check more of this as the semester goes on, but it's our technical difficulty number one with GitHub. I don't know why you can't merge your conflicts yourselves. Maybe the GitHub Classroom rule is they want the teacher to do it, which seems annoying if there's 80 merge conflicts for me to do. Anyway, so just keep an eye out for that with the GitHub stuff. We're all somewhat learning GitHub at the same time here in that I've used GitHub a lot in my own personal life. I've used it in units before, but there are some little gotchas with GitHub that we're discovering through this unit with our virtual machines and stuff. So just be patient and we'll work our way through it. Quick update to remind you to follow rule number 1, which is to set your Discord username. You don't have to use your actual real life name or your legal name. You can use whatever name you want, but so that I know who the heck you are in terms of UTAS, please do as, say, Armin, John, Jang, Jotham, Josh, Alejandro, and Zach have done. You can see all their excellent names in the chat there. They've got their UTAS username in brackets. Yes, put your social security number. We used to put student numbers and then we got in trouble for that, because that's a number that means something apparently. If you're asking me a question on tutorial questions chat, please do. And there already are some, which is excellent given it's only the start of week 2 now. But just so that I get a notification straight away and I don't have to browse the Discord to spot it a few hours later, please @ me so that I get a notification. I'll still see it anyway, but just for whatever reason, forum posts, I don't get a notification on my phone when they get created. I do if you put @Lindsay Wells in there. Still getting emails about I can't make it to a tutorial or I'm not allocated. Those questions are never for your unit coordinator. They are always for ICT admin. However, just quietly on, if you're worried about tutorial allocation, please just show up to a tutorial anyway. Yes, they might be close to full, but they very quickly become not that full during semester. Enough people are using their laptops, the room's big enough, you will be able to work with your tutor in there in some way. Plus, I'm the Hobart tutor, so just go for it, right? But yeah, eventually you need to get your allocation sorted out. That is all to do with ICT admin, not me. Those of you with eagle eyes might have noticed that at 11 o'clock last night I changed the slides. I've re-uploaded weeks 1, 2, and 3. There's no new content, it's just a shift of where the content is, because last week we didn't get to the cloud computing stuff, and I also wanted to just adjust the structure, the order in which we talk about those cloud fundamentals things. So no new content, you haven't lost any content either, but just have a look. If you're the type of person that downloads the slides and likes them being in sync, you need to download them again. If you do download the slides, which I recommend, it's better to watch in PowerPoint than in the browser in Milo, because we saw that it looks ugly. One, I fixed that problem. Someone had a post saying that one of the things looked ugly for the cloud computing stuff in Milo. But also two, just open up in PowerPoint, because there are hidden slides where I've decided I ain't got time to deliver that slide. If content is not in a hidden slide, it means it's not going to be assessed on any kind of quiz. But it's there and it's useful because you get a little bit more information. But yeah, you will notice there are hidden slides in some of the things. That's all I want to talk about for housekeeping. I went through pretty quick because I'm trying to catch up on time here. Does anyone have any questions about the unit at this point before we actually get some content happening? You can ask questions at any time, even outside of lectures, of course, but you can get an immediate reply from me if you're worried about something. I forgot to put on this slide preparation module. I've put the preparation module now also up for everyone instead of a separate Milo site. Probably that's what we should have done. The reason preparation module was a separate module was so that the diploma students could do it before the Milo site for this unit opened. But now I've just made an entire copy of the preparation module. All students, BICT, MITs, can see it as well. It's not assessed. There are quizzes in there, I think, to test your own knowledge, but it's just there for your own reading. Also on the housekeeping, online tutorial, you should be able to see the tutorial room now if you're enrolled in it. So if you can't, just DM me. It's a 5-second fix. But if you can't see that link that I just put in the chat there, and you're supposed to be able to go to the online tutorial tomorrow at 3 PM, send me a message. Alejandro's got a question, so I'm going to use this as a chance to sip my Coca-Cola. But still wondering why on earth my camera's not working. It's making me sad. I want you to see me. I'm happy-ish. Yep. The way to acknowledge AI, Alejandro, will be or is explained, I think, in the assignment spec. Each time, uh, whatever way acknowledges the fact that you've used it. So if you've used ChatGPT, I would implore you to share your conversations. I realize that sometimes isn't possible when you've got image generation in your chats, but otherwise, if you're using something like Copilot, which is doing inline changes, just add comments into your code to say this part was AI generated. Just as long as there is sufficient evidence to say you've used AI and where it is, so that we know that you're using it. I'm not picky about how this is done. There's no hard and fast rule. Just you need to vaguely acknowledge it in some way. Great question, Alejandro. The entire thing. No, it needs a bit more specific than that, Armin. Yeah. Yeah, absolutely, Alejandro. All right, so content. We have a few different sort of little modules of cloud computing fundamentals, which will be shown at the start of this one, and then a little bit more at the start of the next one, as long as we stick to time. It's not looking good though, so we'll see how we go. Then the next, effectively, the two parts here about networking protocols and web technologies. That's where it's going to feel hopefully very comfortable to the students in the BICT and Masters, because we're going to be rehashing some stuff that you should already know around HTML, PHP, what a TCP/IP is, that kind of fundamental stuff. That'll be brand new for some of our diploma and grad cert students. Those things are underlying technologies that some of it you'll need to know and just have as background knowledge, background noise in your head. But otherwise, it's just setting the scene. It should be a relatively easy start. Then we're going to talk about Model View Controller. We're going to start talking about that in preparation for this week's tutorial. So we'll see how far we get through Model View Controller in terms of actually looking at the code. We'll talk about it at a high level and we'll get that done. But really, the implementation of Model View Controller for this unit is best done and experienced yourself in the tutorials. We'll see what I can live code given the time remaining. So let's dive straight into our first bit of cloud computing fundamentals. Some of this stuff here we'll look at a high level, and then we will revisit again in various times throughout semester. I don't know why there are drawings there. So just to start the entire thing off with a description or a definition, the Oxford Dictionary states, no, not quite Oxford Dictionary, but it is highlighting what cloud computing is. This is best explained through the characteristics that we'll see on the next slide. But the idea of cloud computing is that it's a model for making on-demand network access, right? So things are immediately available, they scale up, they've got a shared pool of configurable resources. So these might be servers, these might be storage buckets, databases, applications, generally just some kind of services that are provided, and that these are rapidly provisioned. So they're made available as soon as you request it. They're done on scale, and there's all sorts of different characteristics around that. We say 5 characteristics. I think we list 6. We'll talk about service models next week, and deployment models. We may or may not actually bother talking about them because it might be TMI. But the deployment models that we're talking about there are private cloud and public cloud. Those mostly serve to be quiz filler though, so we'll see if we bother talking about that. Service models next week, essential characteristics this week. If we want to really simplify it, it's ICT as a service is one way of saying cloud computing. So there's lots of providers out there. It might be AWS, so Amazon Web Services. It might be Azure like we're using. It might be Google Cloud and all the Firebase stuff. It might be Nectar Research Cloud, which some of you have maybe heard of. All right, these are cloud providers, and they are provisioning the stuff that you need to make what we call web services. Web services are effectively going to be what you're building in this unit. That's the focus of this unit. So we're going to be much more on an actual web service and a little bit around what the provider provides. There's only so much we can do in this purple box itself because we only have access to Azure Labs, but we'll be talking broadly about what goes on in the cloud. But this diagram is one that I've thrown together to try and situate you as an end user in relation to what the cloud is, right? Because we've always seen this sort of diagram of a user, and we've seen the cloud, and there you are just talking to the cloud. But the whole point of the cloud is that it's this big black box and we don't know what's in it, right? Well, this is kind of the big black box. It's not very much more of a diagram than that, but we'll be deep diving into what the providers here do provide. You consume and use these web services. These web services are created by developers. So hopefully you'll go from you being an end user all the way over to you being a developer at Netflix or something like that, right? Creating web services that are provided by these providers. And the communication here, a bit tongue-in-cheek, but everyone's harvesting your data. So, the developers are paying the providers, you're paying the developers, and you're paying with your life and your data. If we wanted to add another line here of, what's the cost involved in this? We talked about those characteristics of cloud computing that try and underpin what cloud computing is all about. So this is going to inform us of, we're going to talk about these characteristics, and then throughout this unit, we're going to try and cover at various points, how do we make these characteristics come about? So what are the technologies that make this happen? So we saw in the definition there that cloud computing is an on-demand thing. So this means that consumers expect to be able to access and monitor their their computing capabilities, their networks, their servers as needed. They can access these immediately, though I think that's another characteristics. So, these are on demand. They're out there in the network. They're a large network, so the cloud isn't just your grandmother's LAN. It is it's a much larger network. Various clients throughout the world on PCs, laptops, mobile devices, any kind of client software, including other servers, can access the capabilities over the network. This network, though, is more than just outside clients being able to access a single server or a set of servers. We will see later on with load balancing that the cloud might have what we call edge servers, right? That, yes, our users are connecting to those servers, but then behind the scenes, there's all sorts of microservices and other virtual machines working together. The database itself might be inside there, or definitely would be inside there, all hidden away. There's no way for a user to directly access these services, right? So that's not possible, but they access it through these edge services, either through externally facing dashboards, APIs, that sort of thing. And so the cloud abstracts away all these microservices, all these other things. It abstracts away all the load balancing, all the authentication, and that sort of thing. And so the end user still sees what we're used to, that we talk about in traditional networking, this client and server model. But there is a large network going on in the cloud behind the scenes. We're going to talk a little bit about multi-tenant characteristics of cloud computing here, in that all these amazing resources, these large-scale resources, both physical in terms of actual servers, they got to live somewhere in server farms, and virtual resources, which we'll talk about in a minute as virtualization. These resources are shared and assigned to different tenants, right? This is done dynamically through the concept of scalability and elasticity. We're going to talk about elasticity and scalability next week. But we have multiple tenants that may be sharing the same resources. However, those tenants, those consumers, so those consumers being the developers and also you as the end user, right? The people outside of the cloud, they generally don't know who their neighbors are. It's kind of like being in a strata unit or a flat or a set of apartments, but you have no idea who your neighbors are, but you're all still using the same, pool, if that makes sense. You're all jumping in the communal pool, but you don't know who they are. I'd prefer that in a strata, just quietly, but I don't know who they are. But the idea is that you have no knowledge or control over that, and you also have a very high level control over the location of your resources. So often legally and ethically, a lot of countries require you to store your data and make sure that it stays onshore, right? So A lot of Australian companies will ensure that their cloud services are in a server farm in Sydney or Melbourne, or even with Nectar, you can say Hobart. But a lot of other things might say, okay, you can't have your data stored in the US because there might be legal jurisdiction there that means your data is at risk. We will talk about that right near the end of the unit in week 12 and 13. So yeah, this is multi-tenant concept as well. Because of the needs of the consumers here, the demands of the consumers, these computing capabilities need to be able to scale up in and out. So while there's high demand, say on Netflix, when Squid Game Season 3 came out, they would have scaled up their infrastructure. But then the week after, when no one's watching anything and everyone's cancelled their subscription, they would scale it down based upon consumer demands. And this is generally done dynamically using different approaches that we'll talk about next week. However, as far as the end user sees it, no matter how many users connect to it, as long as the elasticity is right, it appears unlimited. That we just think, oh, Facebook just can handle an unlimited number of users. No matter how many people we throw at it, it just works, right? So these resources, even though they are finite, everything is, they appear unlimited to the end user. Part of that is ensuring that the cloud feels available. So we'll talk about availability rates later on. But the moment that someone requests some servers to be spun up, they need to be immediately accessible, so on demand. But also our end users need to experience no delay when using them, right? So even though the number of users might scale up on Netflix when Squid Game comes out, we as users would not expect it to be slower to download or to stream things off Netflix in those times of high demand. They should be provided immediately and quickly. And yeah, this one is still talking more about the fact that those capabilities, those say maybe virtual machines, those databases, those storage buckets, they're available pretty much immediately after you've said, okay, I want to scale up or I want to purchase a cloud, cloud service. So these need to be immediately available and they need to remain available as well, despite peak demand from consumers. And finally, I assume this is the one that didn't count as one of the 5 characteristics in our NIST definition, is that these are pay-as-you-go. And so this is a bit of a double-edged sword, right? Is that users with low demands will ideally pay less than the bigger companies like Netflix and Facebook and that sort of thing, right? But in that these things are metered. But this can be very tricky from time to time we all hear horror stories of people accidentally getting massive cloud bills, although now those stories have turned into massive AI token bills because they're not understanding what they're doing. However, yeah, you pay based upon how much you've used, and it allows for a bit of a freemium model as well, which when done properly means that you're able to experience the cloud at that little low scale where you have 1 to 10 users, and then once your thing appropriately scales up, you get appropriately charged. A lot of these services now have absurdly complex monitoring and reporting capabilities, the ability to do budgeting and that sort of thing. Despite those tools existing, it is still very easy to accidentally go over your budget. Or, if you do put a budget in place, then you do risk running out of quota, for example, so that new requests from end users end up getting denied. Yeah, Josh, elasticity is an interesting term to think about. We're not going to talk about it today, but we always hear about scalability, right? That, we've just got to be prepared to make sure that our amazing new to-do list apps that we've just deployed onto the Google Cloud is ready for the 100,000 users they're expecting. Oh yeah, that's great. That's scaling it. But it's that elasticity to say, okay, well, our 100,000 users are all in Australia and none of them are doing to-do list things in the middle of the night. So we want to, reduce the amount of capacity of our virtual machines overnight. And we want to do that dynamically. But we want to get the timing right of that, and we need to have nice elasticity. And it's that rate of change. I guess elasticity is, to some degree, the rate of change or the derivative of our scalability of how much we scale in and out. It's an interesting topic for sure, but not one for today, sadly enough. So those are those characteristics that make up the web as we know it now, and they're largely consumer demand related, because the cloud is what we think of and what we turn to when we're trying to make web services that are scalable and accessible. We have to think about what are the technologies that enable the cloud to do all that, right? So there's more beyond what's on this short list, including load balancing for a start, which we'll talk about next week. But we'll talk a little bit about the architecture of these things, as well as I think today will be tenancy. Apologies for not having this list. I mean, these are more concepts, and these are the enabling technologies. The three that are listed here are what we call technologies. Load balancing and tenancy, those are more, I guess, actual... these are architectures, and these ones are more the technologies, the systems that are deployed there. That's a bit of a tenuous link there. These are all jumbled together as what makes the cloud happen. So let's talk a little bit about service-oriented architecture, and let's call it the iteration, the improvement, its evolution in the form of microservices, and then we'll take a bit of a detour to virtualization. So for many of you, this is terms you've heard before. We're not going to go into a huge amount of detail, but hopefully enough to unpack these just a little bit. And then after the break, I guess it'll be, we're going to return to something a little bit more familiar in terms of just the lower level technologies of HTML, PHP, and that sort of thing. So if you're particularly our grad cert and diploma students going, wow, we're jumping straight into some terminology here, don't stress. We're also going to take it easy for the second half of today's lecture. And I think we're catching up on speed here, so I'll try not to go too fast, see how we go. So service-oriented architecture here is basically a collection of different services that communicate with each other. And we've got some diagrams here in a minute, but this has largely been a thing that's come from enterprise overall, right? So it's been around for a long time. The easiest example for something like this to think about might be that, having all the different services that make a bank work, for example, right? So they might have services for their ATMs. They might have services for their loan managers. They might have a service for managing accounts and all these sort of things. They might have very separate monolithic services that are doing things, and they need to communicate with each other. But famously, one of those services for the bank might be running on COBOL or something from the 90s, whereas maybe one of their more newer systems that their loan managers use AI to predict things might be running on a more modern-ish server, like a LAMP stack server, right? Those separate things need to communicate with each other, even though they're wildly different beasts. They're servers that are using completely different operating systems and different things like that. So they have components that they might share, that they might all talk to a single database that is done in Excel or something like that. But they're all integrating in some way, but they're all heterogeneous, which is just a dumb academic word for meaning that they're different, right? They're completely different, gigantic servers. But they're doing entirely big, different jobs together. They're top-level enterprise tasks. And so we need web service technologies, which we'll talk about today, in order to implement this, to make them talk to each other. So to make these things interop, we might use a thing like SOAP, which we will get to practically in week 12, but we'll talk about around week 6 or 7 in terms of just the theory of it. I might move that, I'm not sure yet, to line them up, because SOAP is something that is kind of archaic. We're going to look at it as a example, but instead we're going to use a much more common communication tool called REST for communication. There's nothing stopping a service-oriented architecture maybe using REST, but SOAP is much more suited to these heterogeneous platforms, particularly these older-based platforms in enterprise. We'll get to a diagram very soon around what a service-oriented architecture might look like. But as I said, microservices architecture is something you've probably heard of a little bit more. And you might have heard of it a couple of years ago when Twitter was being handled by Elon, for example, and they talked about all the different services, and he found all the waste in there in the same way that Doge supposedly did. That he not accidentally, but deliberately turned off various services, thinking that they were bloat, and it meant that some aspects of the website or the web application that is Twitter stopped working because he just sort of turned off various microservices. But the fact that you can do that meant that there were these microservices, these different little virtual machines or databases and stuff like that are all intermingled and interconnected in order to accomplish different tasks. But with a microservices architecture, you can swap those in and out as needed if you want to change their implementation. Right? So it's a bunch of small and independent services that are ideally self-contained, although I guess with that Twitter example, if they turned off some of those services, they're inherently interacting with each other, but maybe there was a bit of dependency going on. There would be a dependency between these services. They've got to talk to each other. But the difference between that and SOA is that the services that are being provided here are smaller, but they're also at an application level, right? An example might be, and I think we've got a diagram of it soonish, is that it might be, you might have a service for authentication, or you might have a service for managing the upload of photos. And those services can then easily be swapped in and out because you might want to change how you serve that photo uploading aspect. And you just switch that out. You don't have to modify the code of a monolithic application to swap out the way or modify the way that you're doing uploads of photos. You just swap out that microservice architecture. And the old one and the new one can coexist while you're slowly moving over to the new one and you're testing it. It's the same way that we talk about modularity in terms of our applications. That's the idea that we try to strive for in our applications. But at a higher level, that we've got services that are in charge of small chunks of an application. So that was lots of words. Let's actually talk about these in diagram form. So monolithic stuff, this is what you've probably been doing in 502.202. Your whole application, one big lamp stack, done. Chuck the lamp up on the web. We're sorted. Ship it, it's done, it's monolithic. People do this, right? And have for a long time. That your lamp stack with your PHP code and your database, it's all in there. Your shopping application has the database on there, the checkout aspects on there, the authentication's all in there, it's all in one spot. But chat, what's the problem with doing that? That all the things are in there. You've got your cart, you've got your product database, you've got your orders, you've got, as I said, the authentication is in there. Whoops. What's wrong with this monolithic thing? All the eggs in one basket. Take one down, you take it all down. Yep, something goes wrong. Absolutely. So obviously if auth fails, then you can't get to the rest of the app. But say you've got a small little bug with how you display your products, and for whatever reason, it's a bug that's included in your monolithic PHP application, in your initialization code, and it just kills everything there, right? In the same way that Avery's Wi-Fi just died and everything else on their computer broke in that monolithic system. We break one aspect of that monolithic code and everything else falls apart too. And the users that weren't even trying to do things with the product aspect, they just wanted to manage their orders, they're unable to access it. It's also harder to scale this sort of thing as well, because maybe the thing that's serving your images is the most heavy part of this application because it's got the most bandwidth. But how do you allocate bandwidth to just that part of the PHP application, or the requests coming to that folder? If your product images were coming from a cloud bucket instead, though, then you can get that low latency needed and the caching needed for product images, right? So we don't get that with monolithic. Service-oriented architecture is getting there in that it's coarse-grained, that you might have, as I said, a service that's just for you know, in the bank for the loans part of the bank, or maybe you know, you've got something for your actual, you know, transactions and that sort of thing. But each one of these has their own, say, gigantic set of things, and they sometimes talk together. Right? But they're just a larger set of monolithic tools. Whereas, as we've said, for microservices, they're much smaller, and you can swap them out, or if one bit breaks, it doesn't necessarily affect all the others. So over on this side is SOA. Sorry, my pen is a pain. And over on here is microservices. So the different sort of services that you might have here are these application services. So these are your front end services for the website or your mobile app. But you might have ones that are used to manage your databases. You might have some enterprise stuff to keep everything secure. You might have things for all the transactions. They're large, different services with different users and teams managing them. Instead, you have, in microservices architecture, just a bunch of different things that are either for managing infrastructure, like getting access to the databases, or things that are functional, that they're actually, you know, this is in charge of your API for things. So maybe you've got an API for managing orders, or maybe you've got an API for managing products, or maybe you've got something that provides infrastructure in terms of a bucket for your product images, right? There's just two different types of those, and these are managed overall by different parts of the team. This requires a lot of communication between services, but also communication between teams in terms of our service-oriented architecture. This one just requires different development teams. So it's easier to manage is the idea. So diagram example here of SOA. They still have this concept of shared services, so shared components, I should say, that they might be all interfacing with the same databases because they all need that. But it's possible still that some of these services have their own databases to manage things. But in terms of people interacting with this, you know, particularly someone in a browser, they're going to need still some kind of edge node to work with here. And this is generally abstracted away by the concept of an enterprise service bus, which then takes the requests from a user, and this might be end users, it might be employees, whatever, and routing them to these different providers, these different aspects. But it's this communication here between the enterprise service bus and the services, and this communication here between the databases and the services themselves, that these all might be very wildly different communication tools, different communication protocols, and so we might need something like SOAP that we'll talk about much later in semester. Instead, for a microservice architecture, again, this is an example here for the different services that you might need for a shopping application, right? So your authentication service or your account management service, your inventory and your products, your shipping service, so the thing that's actually in charge of managing when orders go in and out. These are all in charge of their own small chunks of the application. There still is a gateway, which is similar to that ESB that we saw on the other side, but instead we might have a service that's just dedicated as an API for our mobile apps or our storefront app to communicate with. I'm not sure if I fully agree with this diagram here of why the storefront web app itself is talking directly to these services. Oh, no, sorry, I do. My bad. I should have looked at my own diagram. There's something key about each one of these services or each one of these nodes, right? In the little yellow boxes is we've got these RESTful APIs. And that's what we're going to learn about, we'll say week 6 or 7. These are a API that's done purely over the HTTP protocol, and it means that we can make requests to each one of these services in a common way, and we get data back in a common format, like JSON is a common output of our RESTful APIs. It doesn't have to be, but it usually is. It means that something like our mobile app can talk to the account services and that sort of thing, but differently to our browser, right? So our browser is our client talking to a web server, which is just managed by our service here, our storefront web app. And that itself might be making its own API requests directly to those services. Our mobile app itself, it doesn't need anything to serve the website. So there's a communication here where over HTML and using HTML and stuff like that, that gets served to our browser. Our mobile app itself has all the client stuff already downloaded on it. But it is still making requests, just that we might abstract that away using an API gateway, right? And that API gateway takes all the requests that a mobile app could possibly want, like maybe a request is list all products with a search filter, or it's post, so that might be getting things, or maybe it's post a new request to add a product to my cart. And the API gateway will pass that on to, let's say it was our get all products. The API gateway knows to make a further request to the inventory service. The inventory service can be coded in whatever we want, but it goes and talks to the inventory database, our list of products, gets it back and sends it all the way back to the mobile app. Our web server and our web browser can make the same sort of web requests as well, all through these common APIs. So we'll talk a bit about get and post today, and so keep this diagram in mind when we talk about that in a minute. Cole asks, so to clarify, with microservices, there's no notion of a shared database information like with SOA. Each service maintains only what it needs to know how to function, or are there different sorts of architectures where microservices do occasionally draw from a larger pool of data? That's a really good question. I guess with microservices, it's a little bit, unlike service-oriented architecture, it is actually a little less defined. That this is an example of how you might do a microservices architecture where each one is in charge of its own databases. But yeah, generally the idea here is that if the inventory service needed to know something about the account database, in order to keep this code, so the short answer is yeah, that there generally isn't an idea of shared database information directly, in that there's not one big database for all this. Say the inventory service needs to know the details of the account holder. It doesn't have a direct connection to the database. Instead, it might make a REST API request either directly to the account service or through the API gateway itself to get the information it needs, rather than it having to know and have its own database specific code to communicate with the database. Right? So this wouldn't exist. The reason for this is that maybe the account database is the MySQL one, and maybe this one's a Firebase one, or a NoSQL sort of thing. Our inventory service is a version of the inventory service that knows how to communicate with Firestore, right? And imagine a world where your client, your boss, your CTO, your chief technical officer says, no, well, the account database needs to be changed to be a Firebase one. And so we have to kill off the account database for MySQL. The process of that is we would write a new account service, which still has the same API, so that the API gateway and the storefront, nothing has to change on these guys. They're using that common API that is just well-defined for your application. The concept still remains the same as saying, I want to get all the accounts, or I want to post a new account. The API doesn't change. But the code inside here, this is where you're writing your code that needs to talk directly to the database. In here, this was code that knew how to talk to a MySQL database. In this one now, it's code that knows how to talk to a Firebase database. So that's fine. We're able to appease our boss by removing the MySQL and making a Firebase database. What happens though if the inventory service had been written in a way that had direct access to the account database? Suddenly, your boss's request to get rid of MySQL and add Firebase means that you're changing code in 1 and 2 spots. And it means that you're suddenly having to replace the inventory service. That's not very modular. That makes big, large-scale changes difficult. Whereas if the communication for the inventory service was done, as we just said, out and through into this REST API, well, all we're doing is just changing which REST API we're talking to. But because REST API 2 and 1 here, these two are the same, the REST API, that interface doesn't change. It meant that the code over here on inventory service doesn't have to change. It might, I think the amount of time would be negligible because largely all of this is in its own private network with services that don't have a large latency between them hang. But in the same way that depending on what the communication that was directly between these databases were, what we're abstracting away here is the concept of load balancing, where these databases actually live. Are they all actually on the same virtual machine? Sorry, are they all on different virtual machines on the same physical hardware or not? This architecture doesn't inherently mean that things are slower, but it is meaning, hopefully people got what I just said there, that because we're using these REST APIs, that if we have to write a new account service, this part doesn't change. And if inventory service is just communicating with that account service directly through a REST API, then it means that inventory service doesn't have to change when your boss tells you to change something. All right? That's an advantage of microservices. And it also is more amenable to scaling up different aspects of this. Josh, yes, that's right. In an ideal world, you just tell your boss it's not needed. But, imagine the world just catches on fire one day and says, actually, MySQL had an irrecoverable security flaw and just isn't possible, or it's not compatible with the new world of quantum computing. We need to move to new quantum DB right now so that we can put it on our homepage. It's just going to happen. So microservices enables that. Any questions about this diagram here about microservices? I really appreciate that question, Cole, for clarifying it. Let us go on for the nice tangent there for 7 minutes, which is exactly what I want in these lectures. Not being sarcastic, I do like that. I had fun. The idea here is, this is obviously a fairly, we're heading into quiz fodder territory where it's fairly straightforward to ask questions that ask you to compare and contrast service-oriented architecture and microservice architecture. So just a little bit of a preview here is that maybe not necessarily this slide, but particularly stuff like this, where we talk about the differences between these. What do I want to say here? So microservice architectures are largely functional in nature rather than needing these enterprise-based things. They're application-based. What do I want to say about this slide? Nothing in particular. Yeah, okay. So when we talked, this is useful to know about these different enterprise services and that sort of thing. So what do we mean when we talk about a functional service, right? Effectively, these functional services are for operating business operations, like managing those orders and that sort of thing. It might be infrastructure services are in charge of managing security and authentication. So it might be that you have an entire service that's in charge of managing your user accounts and checking if someone's authenticated or not. An application service would be more fine-grained. And so an application service might be something that's providing the images for your shopping cart, or it might be providing it might be the API gateway service, that sort of thing. An enterprise service, these are all just sort of labels for things. It doesn't really matter too much about, we just love to label things, I guess, in academia. But as I said, these provide entire functionality for entire parts of the business. This is a bit of a confusing slide, I'll admit that, because it's mixing things from SOA versus microservices. What's more important, this is more of a quiz page, just to try to scare you less, is that the quiz question I might ask about this is not for you to list all the different differences, is I might tell you one of these as a fact in the question. And I want you to explain how how come this is the case, showing me your understanding of these things, right? So because we've had this big explanation of them, this is a summary. I want you to work backwards in that quiz question and say, okay, well, you know, when we refer to the simple messaging system benefit of a microservice architecture, what are we talking about here? And it might be that I want you to start talking about how REST is accomplishing that. So microservices are trying to make things as independent as possible. They are focusing on the application itself and the people and the collaboration within that regard. As I said, it's a simple messaging system that uses something like REST in order to do that. It's meant to be lightweight. Each one of the services in a microservice architecture might be single-threaded, whereas those larger monolithic things might be multi-threaded. They tend to use traditional relational databases in terms of MySQL and that sort of thing, whereas we tend to see much more modern architectures with a microservices architecture. This is a big one here, right? Of a systematic change. That was Cole's question, or what we got into when I answered Cole's question of, you know, a big change like swapping out the database implementation requires modifying the monolith very often. It's difficult to get DevOps and continuous delivery in there. Whereas in a microservices architecture, continuous delivery and DevOps, so we're not going to talk much about that in this unit, but hopefully you've heard of that, of where you're using source control and you're using, you know, your developers are updating the code and constantly pushing changes. That fits much better with a microservices architecture because we can make those small changes quite quickly. Not so much, yeah, that's compatible with agile development. It's a software development methodology, but it's more just this concept of if you're making changes to the code, these can be automatically deployed and you can see your changes live. But with that comes the need for separating production and testing servers and that sort of thing. It's a lot easier to do that in a microservice architecture because you have different services for the testing environment versus the production environment. And it just means that changes can be done quickly. And that is necessary, yes, for agile development. So yeah, you can connect those things together. A big part of what we just talked about there for microservices architecture is the need for lots of different smaller resources. We're not going to talk about scalability today, but we'll keep this topic of virtualization in mind when we revisit it next week. Is that we have all those resources and maybe they're quite small. It doesn't make sense for those to be literal servers, right? Like one entire computer networked to another, right? So when we talked about this diagram, this wouldn't be a computer with a network cable, connected between these. They might be in a service-oriented architecture if you've got entire, monolithic servers doing these things. But for these smaller services, because this is a very small example, you might have hundreds of services. It wouldn't make sense to do that. So instead, we can provide virtual resources from the actual physical computing hardware. But also, this is just generally how the cloud works, right? So if you're AWS and you've got a couple of 100 million users or more, or whatever the number is, you don't want an actual server for each one of them, especially if little Joe Bloggs wants to host his to-do list app that's just for him. They're not just running out and buying a computer and plugging it into the power board, right? They're not buying a Mac Mini and plugging that in. They are allocating 1 or 2 cores from their gigantic, massive, multi-gazillion core server farm to just little Joe Bloggs and his to-do app. But how do we do that? We abstract that away from the physical computing hardware resources. Similarly, you got a really small database, you're not going to do an entire hard drive just for that. But instead you might have drives that are petabytes big, but they manage to, chop that up into little chunks for each of the little bits of storage that you need, each of the little databases that you need. But this gets all abstracted away and it still feels like you've got your own computer, which is what we've got on Azure. For those of you that have logged in so far, it feels like you're connecting to a computer, right? It's almost the same as if you have a lab machine and you're connecting to it and it's all yours and the hardware's all yours. But in reality, you're on there with millions of other, not millions, but potentially hundreds of other people on the same piece of hardware. So you can define for your virtual machine the number of cores, how much RAM and how much hard drive space, what your chunk of the pie is, and those can be scaled up and down as needed. But that's largely done by just adding more virtual machines and using the concept of load balancing, which we'll talk about next week. And so, yeah, that brings us to virtual machines, where we have this virtual server that we're connecting to. A massive load-bearing Mac Mini. I love it. We've got Mac Minis in the labs. I can't wait to use them at 12 o'clock and see how it goes. But a virtual machine is the emulation of a true computer. So to you guys, it feels like you're actually connecting to a computer. It runs its own operating system called a guest OS. It's not that there's an operating system called guest OS. It has applications running on that, and we generally define these and reuse these with a concept called images. It's similar to how, I guess we don't use images much other than for Docker these days, but back in the day, you might have an ISO file to represent your entire disk that had Need for Speed 3 Hot Pursuit on it, right? That's an image representing that disk. In the same way, you can represent an image, so you can represent a virtual machine as an image as well. I feel sad that that's what images are now, rather than those lovely old ISO files. But you still do have that with operating systems. You might download linux.iso and then mount that somewhere, right? Utaz Rodham, I assume everyone else can still hear me and it's just you. I realize he can't hear me. Oh, everyone, Josh can hear. Multiple people stop being able to hear. It was only the people with purple names. Maybe I just muted all the no, I'm not going to say that. Well, I'm not sure what happened. It can lag, maybe restart. Unsure. I didn't deafen all the people with the purple role. I promise. I would never do that. So this idea of virtualization is what enables a lot of those stuff from our characteristics we talked about before, of wanting availability, portability, manageability, and security. We're not going to talk about Docker until week 12. Maybe next year we'll be doing Docker throughout the entire unit, but totally agree, Cole. I agree. So virtualization that we just talked about in diagram form here this is what it looks like without a virtualization at all. This is your server. It's a whole computer. It's that Mac Mini that is crying for its life in your basement while you're running 10,000 Minecraft servers on it. So there's your Mac Mini. It's running maybe Linux because you thought that's going to be lightweight. And then, as I said, you've got 100 different applications. All of them are just Minecraft servers, each one for each of your non-existent friends. That's your basement brand, no virtualization. Then we have two types of virtualization. One is where this is called a type 1 hypervisor, where the difference being that a type 2 hypervisor has a host OS, so that still might be your Linux at the top level, or it might even be Windows, right? And you're using these type 2 hypervisors to run different virtual machines. This is your concept of, say, VirtualBox and others that names are on the next slide, right? Where you're running literal virtual boxes on top of a host OS. A type 1 hypervisor, which is much more what you're actually going to see in the cloud, is where the guest OSs talk through the hypervisor directly to the hardware. This is a more complicated hypervisor in that it has to itself be in charge of virtualizing the hardware so that a virtual hard disk appears for each one of these. Some virtual RAM appears for each one of these operating systems. And that's what the hypervisor does here as well, but it has to do it through the OS. From these two, what do people think is going to be more efficient, I guess, in terms of, the most efficient use of hardware. Anyone have a suggestion here? Keeping in mind that this one is working through an operating system. It's running potentially a heavy operating system. Interesting guess. Can't remember what my question was of which one was more efficient, I guess. The idea here is that if our resources are being taken up by this host OS, as well as each one of the VMs here, we have freed up some resources by not running Windows or Linux in between here. So if you don't need on your actual server to have the need of a host OS, then you should go with a Type 1 hypervisor approach. The Type 1 hypervisor itself is more heavyweight than maybe a VirtualBox might be, but it's going to be more lightweight than the combination of VirtualBox running on Windows or something like that. Okay, so where possible, and if it's what's suitable for you, you might use a Type 1 hypervisor. What I've just described there is written in text here. This feels like another quiz kind of thing. I'm not sure if it actually is, but kind of describing the differences here. I pretty much said everything I wanted to when I was looking at those diagrams here, but the idea with a Type 1 hypervisor is that it's running directly off the bare metal, right? It's talking directly to the computing hardware. The guest OSs, each one of them is communicating with the actual hardware. They're both communicating through the hypervisor, just in slightly different ways. The guest OS communicates with the host OS in the Type 2 hypervisor, so it means that tools like VirtualBox, they're running in the host OS, and it's then relying on the host OS's connection to the hardware, right? So the drivers that are inside the host OS are doing the heavy lifting here, whereas in a Type 1 hypervisor, the actual hardware is being directly interfaced by the Type 1 hypervisor. So this feels like there's a lot more overhead, but it has some convenience, if that makes sense. In the interest of time, we're going to take our 5-minute break now, and we're not actually going to talk about single tenant today. I'm going to move these slides into the cloud fundamentals for next week. This is where we lost those 10 minutes at the start, I think. So let's take our quick break now, and we'll be back in 5. When we come back from the break, we're going to be talking not really that much about networking, but more about protocols and the basics that we need to get going in the unit. I'll answer this question now. Is the expectation that we finish the cloud platform during the tutorial, or we can finish it? You can finish it. It feels like the two things you've said there are the same. So the expectation is that you'll have it finished by the start of the following tutorial, right? So particularly this one, because it's got a bit of a large ending to it where you're expected to play around with making your own PHP website. People who are really up to speed or have done a lot of this stuff before, ideally they would get this done by the end of the tut so they can get it out of the way. But for most people, 95% of people, I would imagine, you might need to fix up a few things in the middle of the week and show your tutor at the start of the week 3 tutorial. That's when it's still considered on time. After that, it's late, but it's only a very small penalty. Everyone works through at their own pace here. Hopefully that answers your question. So you should be working on it during the tutorial. It would be amazing if you finish it by the end of the tutorial, but more than likely you'll be showing it at the start of the next tutorial to your tutor. Hopefully that answers your question, Josh. Yeah, cool. It's totally cool if people come to the tutorial and say, I'm already done, to show the tutor. At that point, the tutor, which is me, Tony and Launceston, will say, you're free to go if you really want to, or you may as well start on the next one if you like. I'll start the break now and look at Cole's question about the preparation module. Don't know why you can't see it. Let's have a look.
Australia Day would be complete without bloody Smith's snag chips, mate. You know, later on we're going to have some snags. It's a bit early for that. I'm just kidding, actually. I ate the whole packet before I started recording. That's why I don't have any snags with me at the moment. But these will have to do. Oh, fuck.
Chosen cunt! It was said that you'd pay for the beers, not pinch them. Bring balance to the boys, not leave them with no grog. Fuck the boys. You and me cobber and a cunt.
Australia Day would be complete without bloody Smith's snag chips, mate. You know, later on we're going to have some snags. It's a bit early for that. I'm just kidding, actually. I ate the whole packet before I started recording. That's why I don't have any snags with me at the moment. But these will have to do. Oh, fuck.
You want that? All right. Okay, cool. So hopefully everyone can still hear me on Discord. And yeah, we got my video back. I'm not sure why that worked. Not super. I'm just mad. Just mad. Give me a second. How to turn off that? Go away, prompter. Something over the top of my teleprompter where I can't see what I'm doing, and it's annoying. There we go. Display, much better. Weird. I'm sure there are other people other than just Josh working through things as well. So yeah, don't stress. You're not expected to have started this tutorial at all or anything like that. But yeah. So we will probably just get through to the point of talking about some of the basics of this unit. We're probably not going to get into much detail about the model view controller stuff, unfortunately. But that is the topic of the second half of the tutorial this week. And so that's largely going to be, it's better done practically anyway, so we'll jump back to it next week anyway, which is what happened last year. This always happens. Okay, so hopefully this next part, for many of you, it's either revision or stuff that you've at least heard of. But if it's new to you, don't stress either, because you're going to ease your way into this unit. We provide lots of base code. The online tutorial particularly, which is full of the grad cert and diploma students, will get as much additional support from me as needed. You've got everyone here on the Discord to help you out. But let's take a bit of a crash course, a whirlwind tour, if you like, through all the things that make the internet the internet. So this is what we've seen all the time, right? That we've got our client-server model. The internet is somewhere in between. Generally, we make requests, we get responses. The internet isn't much more than that. It's just that there's lots of them going on, and the internet itself is full of servers that are also making, that's a terrible arrow, requests to other servers in and out through that microservices architecture, for example. So every time we saw an arrow between a REST API and a service on that microservices thing, that's still just yet another request response thing going on there. And in that case, it was generally an HTTP request using a RESTful API. So networks, though, themselves, these computers, they're physical hardware. We're thankfully not touching any of that, but they're generally connected via wire and wireless. I can't imagine what a third one really is, other than maybe quantum entanglement. We'll get to that one day, I'm sure. Clients, actually, I'll list the types of servers, pretty straightforward. File servers, web servers, maybe mail servers. But as we know, there are servers out there in the internet that are talking to each other for different microservices. What kind of clients are we talking about here? Just really quickly, chat, so that we don't run too far behind. We've just said a client here. What could a client be in this concept of a computer network? What client are you on right now, I guess? Generally, it's another computer. Everything's a computer, isn't it? Device, everything's a device. Yep. So it might be a client. Yeah, so that's a good distinction there, though, Josh, isn't it? That it's the application on the device. And this means that we can have a wide variety of devices, but it's, yeah, more specifically, it's the application on the device, which, as James said, it's a browser. What else might be an application? So, yeah, maybe the Android application running in your smart fridge is a client making requests, right? Whereas what Cole said there is some kind of hardware. What's another client? There's one more, at least simple example that fits the bill here. Let's just see what people come up with. Another server? Absolutely, yeah, right? So as I said, maybe you've got a PHP application inside an Apache server, and that can absolutely make requests to other servers and responses. It would. And as Cole says there, Robot Crawler would be an application on your server. We will do that in week 11 or something, right? Another one might be that it's not necessarily just web browsers on computers, but on a phone it might be a web browser on a phone, but it also might be an Android or iOS application inside a phone as well, right? That's making API requests directly to your server, right? And the way that these completely different clients can talk to completely different servers, so some servers might be file servers, they might be Apache servers, they might be Node.js servers, all different things. they manage to communicate with a common protocol, right? So when we talk more about a definition of a network, we say that it's a global networking. It consists of interconnected networks using standardized communication protocols. And so this is where you might have heard of those different layered models where we start talking about TCP/IP, UDP, different services or applications on there. You don't need to understand these to any great level of detail, but we will start, at least at the application level, be talking about these just a little bit in this unit. All right, so these protocols have different rules that are understood by both ends of the communication in order to work. Right, so if we talk about, say, even just HTTP as a protocol, your web browser knows about HTTP protocol. Your Android application knows what HTTP protocol is. Heck, your smart fridge knows what HTTP protocol is. And thankfully, the servers on the other end, Apache and Node, they know what HTTP protocol is. So that means all those different clients and servers can communicate. Whereas if we didn't have these interconnected, standardized protocols, we wouldn't be able to do it. That's at the application level. But then at the more lower level, which we won't talk about this unit, is in order to actually send the data, the bits and bytes or whatever, we need that TCP/IP protocol. So this is just background knowledge here to say this is what the internet runs on, TCP/IP. You know, if you want to know more about this, go to your networks unit. You'll go into a lot more detail there. But these different application layers are how we do things. So we're going to be playing up here at the application level. We're going to have quite a bit of fun here in that you're going to be connecting on the application layer through SSH. You're going to use the HTTP protocol at that level. You'll be playing with the ports at that level. Everything underneath that, your TCP and UDP, this is all, how do those applications actually just send the data through? And then how do we physically do that using Ethernet cables or Wi-Fi and that sort of thing? Yeah, absolutely. Thank you for a specific unit code there, KIT214. Don't know what the master's version is, but this is fairly standard stuff. So if you care, the application level is where we are concerned with the process-to-process communication, right? Your smart fridge is running a process that shows you the crappy list of things in your fridge. Your Apache server, your Linux box out in the world, your virtual machine, is running an Apache server with your PHP code on it. They're the two applications. They're talking to each other, but then at lower levels of it, they're trying to work out how to deliver the bytes into packets. How does it actually go across through the nodes and the wires and transmitting the actual raw bits, right? So that our smart fridge doesn't have to care about how the raw bits are sent. It just worries about things at the application level. At that, in between, there are different protocols that doesn't really matter to this unit in terms of TCP and UDP. So TCP has this sort of receiver and sender sort of handshake. It's all done very carefully to make sure that we know who we're communicating to. We make sure that the remote person is there or remote server is there. And it results in, ideally, no data loss because we want the entire thing through there. There's obviously lots of overhead and it takes a long time to deal with making sure that baby gets sent. But the UDP one, the baby might be sent, the data might be sent, but it also might not. And it might not be intact and it might not be in order. But UDP, super useful for obviously network games and low latency things. But for our purposes, we're not even going to consider the differences there. It's just almost just about an excuse to just put this meme into these slides. So those high level protocols, we talk about ports. Again, the specifics of port mapping and that sort of thing is more for your networks unit, but we will, on the next slide, play with ports a little bit, more through necessity than anything else of Azure, but it does come into security that it is somewhat useful to understand all the different ports and services that we're exposing on our servers. So ideally, we expose as little as possible to the outside world. We don't want our servers just lying around with file transfer protocol open and possibly able to have the password be guessed, if we don't actually need it. So what to say here? HTTP protocol, which we'll talk about in a minute, uses a default port of 80, but you can use any port. We will be showing you that in the tutorials pretty much straight away. HTTPS, the more secure one, which we'll talk about in a couple of weeks, using 443 by default. Weirdly, port 22 for SSH, not even on this slide, but that's the default internal port that we're using there for all these services. The aside here that I don't want to go into too much detail, but it's something that if you're already familiar with ports, the one weird thing about this unit will be that you'll notice that we're not accessing our website through port 443, right? We're having to add a number onto the end. When we're doing the SSH traffic, we're having to put a number onto the end as well. That's because our Azure labs literally only have 2 ports open to the world. One is designed for that SSH traffic, so that's where you are using VS Code in this unit, and we're overloading that in order to get us to do file transfer as well. But it's also your terminal connection. So we're using that as needed, but we're not using port 22, we're using whatever port the virtual machine is configured with. And then the other one is for remote desktop traffic. So this Azure Labs is actually supposed to be like computers that you use, where you've got a GUI to remote desktop to, and I'm sure you could actually try and connect a remote desktop to it and see what happens. I'm sure you might get a Linux GUI to play with. I haven't actually bothered to do that, but I assume it's there. The first thing we do when we turn on our Apache servers that we're going to talk about in the tutorials is we overload port 3389, the internal port that's normally used for remote desktop, and we chuck Apache onto there. Apache being our web server. And later we'll do Node.js for another way of serving web traffic. And so this 3389 then maps to an external port, which for some of you is like 7001, 7002. So when we make requests into our Azure lab, instead of getting remote desktop traffic, we're getting HTTP traffic, and voila, we have a web server running on that port instead. Nice, Cole, great. Don't know what any of those words mean. I'm sure there's at least one person that's mentally high-fiving you there for that. So the short answer here is that don't stress too much about ports, other than that for this unit, we've just got a little bit of funniness where we've only got 2 ports open to the world. That is somewhat a security feature, that we're not exposing a million ports that we could accidentally leave services open, which means that, people could accidentally come in or deliberately come in and view our files and that sort of stuff. So it's quite locked down. It's going to be slightly annoying throughout semester for 1 or 2 of our activities, but for the most part, it's just a little extra gotcha. So as we said, the World Wide Web, the internet, but more specifically the World Wide Web, the stuff that you interact with through your web browser, is largely accessed through the concept of HTTP. And in future weeks, we'll talk about HTTPS and the secure version of that. But that's more just a layer on top of it. In that traditionally we play with the concept of HTML, right? So now we're slowing it right down to stuff that some of you should be either familiar with or are just starting to come to grips with, that generally what your web browser wants to see and work with is HTML, those little tags that mean that you can put stuff in your web browser. And that we use hyperlinks, haven't heard that word in a little while, but we use links inside our web browser to navigate between web pages. When we click on a hyperlink, generally it means that we make a new request for a new page, we get that page back from the server, and away we go, right? And so we just make a bunch of requests over time to our HTTP server from our web browser. That's our client software that's in charge of making those requests and handling and displaying that web content. But as we talked about a couple of slides ago, there's more to the internet than just web browsers making HTTP requests. And we will discover, hopefully, as much of that as we can in this unit. The web server, right? is listening to those requests over TCP/IP. It's serving those client requests. So when a client requests index.html, it will give it to them. Or if a client requests it .php, it will run the PHP code on the server, blah, 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 and then still give back an HTML output. Is what you're used to, right? From 502 and 202, is that you've got an HTML, so we're still getting HTTP, getting HTML response from our PHP code. And it means that our PHP code is relatively secure because all that execution, the details of it, the script, the content of that all stays on the server. We just see the output, right? So this is an inherently, by having secure server-side code running, that's an inherent level of security. It's not everything. We have to do a lot more than just say, oh, our code runs on the server. But it means that we're not exposing to our end users that want to, might understand source code. They're not seeing how the output is generated. They just see the output. And so the web server that's doing that might be Apache. It might be Node.js. It might be any number of others. And it goes PHP, and then it outputs HTML, just to clarify your question. Alejandro asks... Yeah, okay. So, look, this is a good question around embedding PHP code in HTML or directly make PHP code with HTML in it. So from a security standpoint, doesn't matter, right? Because the PHP code is always run on the server, right? And so it will always just output the eventual HTML, or as we'll learn later in semester through REST APIs and stuff, it will output JSON or another format that doesn't have to be a web page. But in terms of what Alejandro is talking about there, we'll see some code listings in a second, is, do we just write an HTML page and then we have little chunks of PHP inside it to replace that part of the HTML with something server generated? And I don't know what you've been doing in KIT214, 502. My feeling is generally it's like you've got an HTML page that starts with an HTML tag and it's got a body tag, and then various parts of the body you might generate, say, a table, right? And it happens in place. That's not actually, for the most part, best practices. I don't really want to preach best practice or not, because it's more, I'm a big believer in just do whatever works. But what we'll try and show in the tutorial this week and in the slides we're not getting to today is that if you use a more structured way of coding, like model view controller, where the view, which in what you're talking about there is the HTML output, that's all done separately, that all that HTML is sort of defined all by itself in a views folder, but the actual logic for connecting to a database, which is our model, and our controller, which is in charge of, making requests to the database and handling all the data, that's all in these self-contained PHP files that don't have any HTML in them, right? And then it finally outputs through the view files some HTML instead. So the more you can separate your PHP and your HTML, the better, because what we'll try and mention at some point this week, either in slides or the tute, is that if you've got all these pages that are spaghettified of PHP and HTML intermingled, how do you then use that same code to output JSON for your wonderful REST APIs that we're going to be talking about? It means that you have to rewrite all your PHP code, and somehow, you end up with duplicated code and stuff like that. So if you can separate all your PHP code that's in charge of handling your data, getting it ready to turn into HTML, then you can change it so that it just, instead of spitting out HTML, it spits out a JSON instead. And that's the concept that I've done there without a diagram of model view controller. We will keep that question in your mind, Alejandro. We will answer that specifically in the slides later. Okay. It's a really good question, though. I love it. So those HTTP requests and responses. This is all the internet is. Just a million of these going on all day night. Our browser makes a request, but what does that actually look like? it uses the HTTP protocol. So it sends a HTTP request to the web server. It's got all these components we'll talk about here, but that request might contain, or definitely has to contain, I want to get something, or I want to post something. Talk about that in a sec. So it contains our verb. It contains a URI, which is here. That's our show me the guide index.html page. So that's that guy. And doesn't really matter, but what version of HTTP protocol, because they iterated over time, that has to be in there overall. We might send some other things with our request. In this example, we don't bother because there will be some headers. You're trying to not show too much on one screen here. But largely our request is made up of a verb, a location that we want to interact with, and the version, as well as some extra request information. The web server, Apache, Node, whatever, can read that and it will spit back to you an HTTP response. So it's going to have the version in it to say, yep, we're all talking the same language. It's going to have a status code, which is very important to this unit. Status codes meaning that either it was okay, or maybe you've got an error, or there's different kinds of errors. And so that comes in our response code. And then the actual, some other headers might come through that we can use to say, how up to date is this information? This helps us with knowing things about caching. So you might get a header to say, this content can be cached and reused on the browser side up until this specific date. Right, so you might get a response header that tells us that. And that if you make a request after that date, you need to make a new request. All right, there are other headers we'll talk about in a sec. And then the actual body, which might be HTML, might be JSON, might be something like that, comes through in the message. All right, that's where the contents of our index HTML comes in. That's where the outputted HTML from our PHP code comes in, is through our response message. Our browser knows how to read an HTTP response and do something with it. You want to see a million HTTP requests and responses? Go to your network tab in the inspector in Chrome. We're going to be playing with that in this unit. That's the general gist of HTTP. It doesn't have to be just sending HTML, right? So the H in HTTP lining up to H in HTML is a bit of a, I don't know, I'm not sure the word here, but it's not actually connected necessarily. Yeah, we request and receive a lot of HTML, but we also receive and request a hell of a lot of JSON, or we might receive image data, or we might receive some binary data representing our Unity WebGL project, right? Heaps of different things, not just HTML being sent over HTTP. So let's drill down into some of those bits that appear in an HTTP protocol. We've got our different types of request codes. There are hundreds of them. We would be hoping for a 200 OK, which means there were no problems on the server. There are a few more others. We will talk more about them later in semester, but there's a range of errors in the 400, like Zach's just said in the chat. 404 is our most common one. While I'm talking through these, someone else mentioned another status code that they can think of off the top of their head that isn't on this slide. But the different levels of 400 here have different meanings, and when we get to REST, it's important, it's a RESTful protocol, it's important that we do send back the right one. That maybe the thing was not found, but maybe it was also not found because we've sent the wrong data to the server, so we'd make sure we send a 401. Or maybe there's actually no problem with the request and what was made, but the server got confused, it tripped over itself, and there was an error in the PHP code, and so we get a 500 error. If you get a 500 error, I've already put something in the references resources chat to show you more information about that. So when we get one of these bad requests, traditionally, and secure servers will usually give you nothing with it. It'll rely on the web browser to show you the 404 little dinosaur error message page, or you can send your own still HTML response that is customized to say, why was your request bad? Or what was the server error? Although that's insecure. If we reveal what the server error is, then we are revealing information about our server-side code. Again, we'll talk about that in future weeks. Thanks, Cole. I'm glad someone mentioned 418 I'm a teapot, which is mostly just there for fun. but you will be made to respond with 418 in assignment 2 at some point. So those are our response codes. Those were things that a server can give us to say, okay, the response was good, you gave a bad request, you've tried accessing something you can't, or the server tripped over itself while you made that request. Your request, though, needs to have some verbiage to it to say, what kind of request are we making here? Are we trying to get information from the server? Are we trying to post new information into whatever the database or the storage is? So we're trying to upload a new registration form, or we're trying to upload a file or something like that. That might be through a post. A put might be to say we're trying to update an existing resource, or we're trying to delete an existing resource. Good servers using RESTful APIs will look at this as a first step and say, I'm getting a GET request or I'm getting a POST request. Better do something different. There are a few others that we won't talk about in this unit that make web browsers work, and they tend to send these automatically for various reasons. Here's what these actually look like. So they're actually big chunks of text that get turned into bits and squished through the wires, but a full request will be in this order with this formatting. So we've got our verb, we've got our URL, we've got our version. We're also saying, what will we accept? I never actually bothered to check this example. We should be probably not trying to accept images or GIFs. So this is a dumb example. I apologize, I didn't actually check. Unless we're allowing all responses. But here we're sort of saying, we're making a request to an XML page. We would also be saying, we are expecting this to come through in XML format. So this is actually wrong. But generally, most of our requests just comes through in that first line. The other things are used by the server. It's useful to send a user agent through. So this stops us detecting, this allows us to detect that a robot is scraping our page, even though the user agent can be spoofed. But yeah, most of it comes through in that first line. Our response is more important here, that we get our status code with the text alongside it, but the status number is the most important thing here. We suggest to the browser how many bytes are in the response. We are saying what type of content is it. So it's saying, hey, we're giving you XML content. That sets the browser up to go, okay, I better put myself into XML mode, or I better put myself into JSON mode. So all of those headers come through to let us work out what to do with that information. And then finally, after a big gap, we send through the actual response. So here we are asking to get some information about our favorite singers, and we're receiving that back in the request. And this is what a RESTful API would almost look like this. We're halfway to a RESTful API here, but not quite. We're making a request, we're getting a response. Any questions about this before we move on to a little bit of code to finish things off? So I'm really hoping that you've seen HTTP requests and responses before, maybe not to this level of detail, because we will be revisiting this. So if I went fast, don't worry. We're going to revisit it when we talk about REST, which is where this actually becomes important. For the first couple of weeks, these requests and responses aren't going to be important, but they will be very, very, very soon. Yeah, we don't have time to talk about IP addresses. We don't really need to care about them. It's a way of accessing our servers, and through DNS is what maps maps domain names to those IP addresses. But that's much more a networking thing. It's not really what we're here to talk about in this unit. It doesn't come into play. Although DNS for SSL certificates we will mention briefly. Here's what I really wanted to get to is these are the technologies that you're going to be actually using, right? So what we just talked about before of HTTP, all those ports, all of those sort of things, the TCP IP protocol and all of that, those exist in the background. You should know that they're there. What are you going to be actually working with? So in this unit, we know we're going to be writing or at least outputting some HTML, right? So it's perfect for our browsers. Our browsers like to interpret CSS to be able to modify the appearance of a web page. So being able to change the background color, change the fonts, that sort of thing. We want client-side scripting as opposed to the server-side scripting that we just said. That allows us to have, interactability on the page, right? So a page like Facebook where you're able to, click the like button and it does stuff. That's all done with JavaScript. We click a button on a page and it expands a menu. That's client-side scripting, where it's all on the application side. There's nothing sensitive about that code and it can all happen in the browser. So it's for interactive elements of our pages. We've got our server-side scripting, which is in the first part of this unit, and what you're currently used to is PHP, where we're handling our data from the database and using it to output HTML. Later in this unit, we'll look at an alternative to PHP, where we use JavaScript on the server side to handle web requests. So that's in week 7, I think it is. It's not hugely important to do a lot of SQL in this unit. We largely give you most of what you need automatically. We're not going to go into a lot of detail here for SQL, but that is one way of interacting with a type of relational database. This concept called Ajax, this is where we make those web requests, but instead of reloading the entire page, we do that with our client-side scripting. So it's our JavaScript, and it's making requests to get some data, which is XML in the diagram here, but could also be JavaScript. So we get, instead of getting an entire page back, we get back some data, and then we use the JavaScript, the client side, in order to handle that response. We're not really going to do a huge amount of Ajax in this unit. Anyone done some Ajax in previous units? Did they cover that in any detail in 202.502? Just out of interest, chat? Ajax being those things where, like in simple forms, it's partial reloading of the page rather than reloading the entire page. Or when I say Ajax, does everyone have no idea? Okay, we have an example of Ajax later. It's very much client-side, which is not the focus of this unit, but I'm happy to talk about Ajax as much as we want in this unit. And then finally, we've talked a lot about XML and JSON being ways of letting humans and machines talk to each other. Sorry, letting machines talk to each other, because most machines know how to read and write JSON and XML, regardless of whether they're Apache, whether they're PHP, whether they're a smart fridge or whatever. They are programmed to understand the standard format of XML and JSON. Yeah, cool. So a bit of DOM manipulation. Yeah. Okay, so let's look at some pretty pictures of some of these things to ease yourselves into it. So HTML, hopefully you've actually been looking at that preparation module if you don't know what HTML is. You're going to have a fun week if you don't. So please have a look here. HTML is all this client-side stuff that our web browsers interact with and understand. So it's a bunch of tags that have meaning to them, and they have a general tree structure to them. That's that DOM, document object model. Who cares what DOM actually is? But it's that we have maybe a header to our page, which is invisible, containing information that the web browser uses, like the title to put on the page, where it gets its CSS styling from, where it gets its external JavaScript from, then the actual layout of the page. So without any styling, we have our body of our page, and then we might have some headings of different levels. So a bigger heading, a smaller heading, series of paragraphs. Each one of those tags then might have some content to mean something. So here it is, what is the text in the heading? Here is the text in the paragraph. Not shown on this page, because this isn't meant to be me teaching you HTML, is you might also have attributes. Title's not a good example for that, where you might add some additional styling to the heading tag. Or maybe you've got a link tag that has a attribute for where does the link go to, using a href attribute. All right? So that's your HTML. We've got CSS, which can be added in multiple different ways. So we can add it in our header as a whole separate file. So you might have a file that looks like this, that contains a bunch of rules to say, I want my H tags to be colored red, or I want my paragraph tags to be aligned to the left. It already is, but colored blue. Maybe I want this specific heading to be different to everything else, and I have some style directly in there. All right, so we're not really going to use CSS in this unit other than to the extent of you want to make your pages pretty, that's fine, but it exists. Got our JavaScript, which can be added in the header through external files, and also adding in libraries like jQuery. We got our JavaScript code that, again, we're not going to do any JavaScript really in this unit for client side, but maybe you've got something where you add a click listener to a button. So when I click this button, it runs some code. So the code that it runs is here, and its job is to find a paragraph called test and hide it, which was this one. So we're able to do what Armin just said in the chat, which is document object manipulation. So we can change all of our tags after the fact. It's how we get our dynamic pages like Facebook and stuff like that. Our PHP code. So Alejandro asks, is it cool to just put PHP code inside our HTML? Well, yes and no. The very simple example here is showing us what looks like an HTML file. But then suddenly there's a chunk of it here in our PHP tag that gets executed only on the server. Right? So our server here is doing our Apache server is doing the job of echoing out some text, so the world's simplest example, but maybe this is making a request to MySQL, and it's doing some stuff, calling some functions. Could be hundreds of thousands of lines of PHP code in here. But what the end user sees in their web browser is they just see the end results. So this is the only bit that's really important to this unit from what we're talking about here, is this is inherently secure, right? What if we've got some passwords in this PHP code? What if we've got sensitive business logic that says any request from Cole should be met with a 404 instead of a normal response to everyone else? We don't want to reveal that information to our end user. Instead, we just want to give them the end result. And that's what we're doing here. This is all they see in the browser, and when the smart aleck tries to go in and look at the returned result, trying to look after some PHP code, they see nothing. So that's the only bit that is relevant here, that we're talking secure, right? Yeah, we don't want Cole to know that we're, checking for username equals Cole, whatever. PHP classes here. So I realize we're running out of time. So I just want to show you these rather than go into too much detail. You're going to play with this stuff in the tutorial as necessary. But, that PHP code that we just saw in the previous slide, it's very easy to start having entire files of PHP that just define a class object, right? So maybe we're defining a person. Sorry, this is the usage on this side. And over on this side is an example of an entire definition of a class, right? So we're saying a person might have a name and an age, might have a constructor. We don't use them very much in PHP. We might have some setters like that to be able to set the data, and then we access them through instances. So this is where, if you haven't done PHP before, I'm hoping at the very least you still understand the concept of object-oriented programming, where you create an instance of an object and you access the fields on there, like their name and their age. At that point, it just becomes more of a what's the syntax here. So things that if you haven't seen PHP before, you might have been used to seeing p.name. So using a dot notation. PHP instead uses arrow notation. Every time we've got a variable in PHP, instead of it being, we always have a $sign in front of the variable name. That's how you can immediately tell some code is probably PHP. Everything here is public, so we can just access them directly through these accesses. There are things available to us to make things more complicated. So if we wanted to make our code slightly more, it's not secure to the outside world, but secure to our developers, is that we could make things private. Means that we can't echo out these things directly. Instead, we have to start writing ourselves some getters. All of those sort of things that you're used to in object-oriented languages, like C#, like Java, even Python. All those things are here, but just with a slightly different syntax. So please rely on your previous knowledge and then go, okay, the syntax isn't that scary. If I'm going through these bits really fast here, it's because you have a preparation module to look at for PHP if you don't know what I'm talking about here. SQL, this is a lot of text, but if you're interested in knowing about the different bits of MySQL, or just SQL in general, is that we have different aspects to that. We have operations for creating and modifying tables and databases. So those are sort of high-level things that you wouldn't want your end users to make requests to do. So those are our data definitions of coming up with what does what are the elements of a database actually look like. So what are the columns and the rows in our tables? Okay. Data manipulation is more what we'll be doing in this unit of running insert queries to add things to databases, deleting things from databases, updating them, reading them. So this is the only one you really need to worry about. In this unit, I will be showing you or providing you mostly with the way of creating data, or you'll use the relatively easy PHP MyAdmin to do it. So this is where we're playing in here. Then we've got some other stuff that is new probably to all of you around data control. So what users are allowed to run these different commands. We will talk about that in week 3 or 4, right? So this part's new to many of you, data control. We won't really be touching to any degree transactions and data integrity. That's beyond the scope of this unit. So know that those things exist, but we're not playing with those. So we are going to be using this and knowing this, and then we're going to be learning this data control. Nearing the end of the slides, don't worry. Here's that Ajax stuff that we just I asked you about, and only one person responded to me say they didn't know it. Please tell me if you do know Ajax. Like I said, we're not going to use it in this unit, but the idea here is that we combine a whole heap of stuff. So we combine those requests and responses in order to get maybe some inside our normal HTML page. We run some JavaScript, we make an HTTP request using the JavaScript instead of relying on just our browser, right? So normally our browser makes an HTTP request when we click on a link, doesn't it? We know that. We click on products.php link and we make an HTTP request, we get a response. Ajax is that we can make them whenever we want. We can make them every 5 seconds. We can make them every time the person moves their mouse. We can make them every time the person clicks on a button. So we just do it through JavaScript, and the JavaScript is in charge of making an HTTP request. We usually get some kind of data back, so we might get an XML or JSON or something like that, and we use JavaScript to handle that response. With jQuery, we would then abstract all of that away so that we don't have to write native JavaScript, because no one likes doing that. An example might be we write some JavaScript to make a request to get an HTML file, and then we have a callback function that says, okay, we got the data back. Maybe that data is some HTML. I'd hope it would be, because we've just made a request to an HTML page. And we chuck all of that HTML into just a part of our page. This is that idea of partially updating the page rather than updating the entire page. That's all Ajax really is that we're updating the part of the page rather than reloading the whole thing, which is what we expect of most web apps. Again, client side, don't stress if this one doesn't make sense. Last two things that I want to talk about here is XML and JavaScript. Sorry, not JavaScript, XML and JSON. These are ways of representing data. So what I've shown you on the screen here might look like a complicated HTML page for you. It's not. HTML is a kind of XML in that the data that we get in an HTML with the head, the body, the H1, the P, the A, that's a kind of XML that our browser understands. But overall, XML can just be used to store information. This is the information representing a Reddit newsfeed for the Formula One subreddit. So instead of getting the HTML version of that page, where they list you all the Reddit posts, you can say, I want to get that in XML format so that, well, why, chat? Actually, help me answer this as the very last thing at 11 o'clock. Why would we want to get that XML or JSON version of the Reddit thing? Answer this one to finish us off for today. Why would my JavaScript or my server want to get the Reddit information as a JSON or an XML instead of getting a nice page that it can display? Because what have I got here? I've got some children. I've got, I suppose the easier here is a bunch of entries in the list, right? A post made by F1 bot, a post made by auto moderator. Why is that useful? Did I die? Alejandro can't hear me. It'll be on the recording. Because we're OpenAI collecting data for ChatGPT. Not a bad answer, Cole. ChatGPT, those others that are scraping data, those are machines that want to understand this data. As John says, extract it. Maybe we want to be able to just understand how many posts are there. Maybe we want to be able to just look at the list of authors. If we just get HTML that's filled with all this crap, like div tags, A tags and stuff, you have to scrape that, you have to read all that and understand it, and it's hard to get consistent data out. Instead, this XML and the JSON would have a schema to say, yeah, you're going to have a list of entries. And then your XML reader, your ChatGPT, your PHP code that's trained to understand this XML code will be able to read this in and turn it into PHP objects or JavaScript objects that it can then do things with. This is much more useful for a machine to read and understand, to make our microservices that we talked about earlier today, to make them work. So that's why XML and JSON are at the absolute fundamental of what we're going to talk about throughout this unit. Absolutely a custom client like a mobile app. So 100% the Reddit mobile app is not a web page. Right? The mobile app that's actually on Android, not the one that you use in the browser, that's a application written in Kotlin or in Swift. And it is making API calls to get this JSON back and use that for its custom client instead of just displaying an HTML page, which is horribly inefficient on a mobile phone. So that's exactly why you would use this, so that your custom client machine, your ChatGPT machine, your whatever, can read this and just do with it what it wants. Hopefully that makes sense. Okay, we've gone horrendously over time. I'm going to restructure the slides a little bit, and what we're going to talk about next week is a lot of different stuff about model view controller, but not in too much detail. We're not actually as far behind as it looks with our slides, but yeah, make sure you get to your tutorials this week. For the online people, I'll see you at 3 o'clock on Wednesday. Some Hobart people, I'll see you in less than an hour. Feel free to be working on this outside of class, asking me questions in the tutorial chat and on Discord. Hopefully we're getting started on the content now. So thanks all. We will try to be more on time next week. See you later.